In this video, we're going to be working with uniform motion applications. So all of this is going to revolve around the idea of using the distance is equal to rate times time equation that we have right here. I had a student a couple years back who decided to refer to this as the DIRT equation, DRT. That works also, nothing wrong with that. But we are going to be working with distance, rate, and time and how we could potentially manipulate this starting thing to get to the answers based on what the problem is asking us. Now we're going to follow a very, very similar process that we did in 3.3 in the sense that we are going to set up a table, we are going to label things in that table, and then we're going to fill that in with some known information and potentially create some equations from there. So I recommend as we are going through these that the setup and the solving of these problems be done very slowly and in parts. You are going to see a lot of problems beyond the 3 that we are going to go through where there is a lot of information and a lot to be processed with this. So take it slowly, write things out for yourself, organize them, label them. The labeling I think is one of the most important parts that shows up in this section. And I would also say drawing a picture for yourself is also quite useful. I'm not much of an artist, but you're going to see at least some simple drawings that you can use and I would recommend using to go through and make sense of these problems. So with that, we have 3 examples here that we are going to go through. As necessary, I would pause the video to write these out for yourself. We are going to go into each of them in a bit more detail, but they're going to give us 3 good examples and indications of the types of distance, rate, time problems that we can see. There are some others that can come out of this and are sort of similar to these, but these are the 3 main types that we will be seeing to at least get the idea of setting these things up nailed down. So with that, let's go ahead and dive into our first example. Our first problem tells us Stan and Kyle like to ride their bikes near Stark's Pond to the beach. Kyle's speed is 7 miles per hour faster than Stan's speed, so it takes Stan 2 hours to ride to the beach, while it takes Kyle 1.5 hours for the ride. Find the speed of both bikers. So we have a distance, rate, time problem showing up here. We have some distance that they're traveling, we have some time, and we're told to find their speed. Rarely do we see a problem say, tell us the rate of these things. They'll say, find the speed or something along those lines there. So we're going to go ahead and start with making a table for ourselves. I think a table is the best way to start with this. And I think the DIRT equation written in the top left corner is a really good starting place. So at the top of our table up here, we are going to list the distance as a column. We're going to list the rate as a column, and we're going to list the time as a column. Make sure you're including the miles that go along with these, or not miles, I should say. I mean miles for the distance, but the units that go along with these. Miles for distance, miles per hour for the rate, and then the time is in hours. So fantastic. If you want to end the table here, you can do that. Don't have to, but it's something we can write in there. Now, with all of these problems that we are going to be seeing for our specific class, we have 2 sets of information with distance, rate, and time that are guaranteed in the problem. In this case, one of those sets of information corresponds with Stan, and the other set of information corresponds with Kyle. So I'm going to write in each of them here off to the side, so I'm going to have 2 rows showing up in this table as well. So I'll have some information regarding Stan, his distance, rate, and time, and I have information pertaining to Kyle and his distance, rate, and time. Now I would also recommend leaving room at the very bottom for a potential 3rd row here. Me personally, I like using a little double line here to separate this out. Sometimes we have a total that shows up, or a total that we are asked about. We do not always use it in every problem, but I like listing it just in case maybe we need to add the distances together. Maybe we need to add the times together in a problem. That does show up from time to time, so I would recommend including this total row just in case we use it. We don't always, but have it in there just to be sure. We should always be given enough information to fill in these 6 boxes that we have up here, though. That has to be given to us to go through and solve these things. So let's now fill in some information into these boxes based on the problem and what it's telling us. So we're told, okay, so Stan, it took him 2 hours to ride to the beach. Okay, so Stan's time is going to be 2 hours. Kyle's time is going to be 1.5 hours, so I can just fill those in there. Let's make that a better 5. There we go. Okay, so what else can I add into here? Well, what do I know about their speeds? Well, we're told that Kyle's speed is 7 miles per hour faster than Stan's speed. So we're looking for these buzzwords still. Faster than, using the right pen here. There we go. Faster than, so 7 miles per hour faster than Stan's speed. Okay, so that means that if I know what Stan's speed is, or his rate, whatever that might be, Kyle's is going to be Stan's plus 7, because he's going 7 miles per hour faster than Stan's. So Kyle's speed is going to be Stan's, which is just R. I'm just going to add 7 to it to get to my final answer there, or my final speed there, I should say. Now we have this last part here, which states, okay, the distance. Have I explicitly been given the distance that they traveled anywhere in this problem? Did they travel 5 miles? Did they travel 3 miles, 18 miles, 100 miles? We have no idea. Nothing in here is telling us the exact distance that they traveled. At this point, I think a visual and a picture goes a long way with helping us discern some very useful information about the distance that isn't always clear in these problems. So I'm going to start here, and you're going to see my art skills on full display. And this is about the extent of what you would need to do. So we're starting at the pond, and then we have the beach that they're traveling to after that. So I'm going to do, we'll use Stan is in black here, and we'll do, oh, apparently it's not liking that. We will do Stan in blue, and we'll do Kyle in red, just for the sake of seeing those. So Stan is starting at Stark's Pond, and he is traveling to the beach. And then Kyle is traveling to the beach also. I'm noticing this thing keeps disappearing. Okay, there it's going to stay now. Okay, so we know that they're traveling at different rates. We know that they therefore have different times that they've traveled. Well, what do we notice about the distance here? Well, what we notice is something very subtle. It's kind of generalized, but it is very important in these distance, rate, time problems. I do not know the exact distance that Stan and Kyle traveled. However, what I do know is that the distance that Stan traveled is the exact same distance that Kyle traveled. So while I don't know what the exact distance is for either of them, I do know that the distance is the exact same. So I can just list the distance for Stan as D and the distance for Kyle also as D, because these are the exact same things. Now, am I going to be using any total information here? Am I adding the distances together? Nothing really looks like it would make sense to do that, so we're just going to go ahead and put a line through it and just say, yeah, we're not going to use that here. Rarely, if ever, do we add rates, so we're not going to end up using that here as well. And do I have a total time, like I add these times together? It doesn't make any sense in this problem either, so I'm not going to use this total column for this particular problem. And that happens fairly regularly with these. We will see other problems where we will need this total row, so I do think it is worth writing in all the same, even if we don't use it for this problem. So let's start figuring out some information here. Can I make equations out of this information? Well, yeah, I can. I have the distance, rate, and time for Stan, and I have the distance, rate, and time for Kyle. So I can go straight across here and say the distance for Stan is equal to his rate, whatever that is, times 2 hours. And what do I know about Kyle? Well, I know Kyle's distance is the exact same, and his can be written as r plus 7 times 1.5. And the step further, the final piece to bring this all together, is noting that these two distances are the exact same. They are equal to one another, which means I can bring these equations together and set them equal to one another, which gives me the equation of this here. I have r times 2 is equal to r plus 7 times 1.5. And now from here, I can go through and solve for the rate that Stan traveled. And to find Kyle's, I'll just take Stan's rate and add 7 to it. So I'm going to do that down over here just because I'm running out of some space. But we'll go through and solve this like we did previously. So based on this, and a process that we went through here, we know that Stan traveled at a rate of 21 miles per hour, and Kyle traveled at a rate of 28 miles per hour. Now again, I really want to emphasize this super high quality picture and drawing over here. But the information that we get out of this, which is noting that while I do not know what the distance is exactly, I do know that each of their distances are the same. We will be seeing this showing up again in our future examples and future problems, but I do want to really emphasize the importance of that in drawing pictures as we go through these problems. For example 2, we are told Dwight works in Scranton, 234 miles from his farm. He wants Mose to bring him a change of clothes after one of Jim's pranks ruined his shirt, so they meet at a restaurant between Scranton and the farm. Dwight and Mose travel 2 hours to get to the restaurant. Dwight's average speed is 7 miles per hour faster than Mose's average speed. Find Dwight and Mose's average speeds. Okay. Now I'm going to start with the picture for this problem instead of making the table. We are still going to make the table like we did previously, but I think the visual for this problem is a bit more necessary than the table at first. So what I'm going to do here, we got our two endpoints, and again, you're going to see super high quality drawing skills here on display. So we have Scranton, and we have the farm. And we're told that, okay, so they're driving towards some restaurant that's between Scranton and the farm. So somewhere in here we have a restaurant. Now, the important part with this, and why I want to start with the visual here, is we do not know where the restaurant is in relation to Scranton or the farm. It could be right in the middle. It could be closer to Scranton. It could be closer to the farm. We don't know. So we can't make the assumption that the distance traveled here is the exact same as the distance traveled here. So if we have Dwight traveling from Scranton to the restaurant, we have Mose traveling from the farm to the restaurant, cool. I happen to have drawn this thing with the restaurant being pretty much in the middle. However, when I'm actually going through and solving this thing, nothing in here has told me how far from Scranton the restaurant is or how far from the farm this restaurant is. So I cannot make any assumptions that this distance here is the same as this distance here. Maybe it is the same, maybe it's different, but we have certainly not been told anything to confirm that they are the same. So, for the time being, we should assume that these are going to be different distances. What we do know is that the overall distance from Scranton to the farm is indeed 234 miles. What we could do, this is the way I like to think on it. You don't have to use it this way, but you could if you'd like to. I like to think of it as knowing this distance, whatever it is going to be different than this one. So I'm going to label this as distance 1. I'm going to list this one as distance 2, purely to show that these two things are going to be different from one another. But what's kind of nice about this visual is I know that the distance traveled from Scranton to the restaurant and the distance traveled from the restaurant to the farm added together should give me this total of 234. So this 234 is the same as the first distance plus the second distance. Now we might look at this and say, well, great, but I don't have any distance, rate, time, or things like that written in there. And yes, that is 100% correct. That's what we're about to do next. But I do know the relationship between the two distances, and that, subtle as it might be, is very important for working out and getting to our final answer here. So let's go ahead and make our table right below. If this thing will, there we go, let me scroll now. So again, we have our general equation here in the top left corner, our dirt equation. We have our 3 columns. We have our distance in miles. We have our rate in miles per hour. And we have our time in hours. Perfect. Now, we have 2 sets of information that were given to us. We have information that corresponds with Dwight, and we have information that corresponds with Mose, because they're each traveling at different rates, and they're traveling different distances. So we'll list each of those in here. So we have Dwight's information, and he'll be the first row. We have Mose information, and he'll be the second row. And then we'll fill in this total for ourselves, because maybe we'll use that here. Okay, so what can we fill in? Well, do we know the exact distance that Dwight traveled from Scranton to the restaurant? Well, we don't exactly know the distance. Do we know its relationship to the distance that Mose traveled? Only that these are different from one another. So I can write in the distance for Dwight as distance 1, the distance for Mose as distance 2. So d sub 1, d sub 2. This little subscript here that we have written in, all that it's for is to label that I have a 1 distance and I have a second distance. There's no actual mathematical operation that's going on there. It's just a labeling organizational tool that we're using is all. So what else could I fill in? I need these final 4 boxes filled in here. What other information have I been told? We've been told that Dwight and Mose drove 2 hours to get to the restaurant. Okay, so the time that Dwight traveled is 2, the time that Mose traveled is 2. Okay, same time of 2 hours. Fantastic. Do I know anything about the rate or the rates that they each traveled? Well, we were told that Dwight's average speed was 7 miles per hour faster than Mose's average speed. So that's some important information right there. So Dwight is traveling faster than Mose. So whatever the rate is that Mose traveled at, I can take that and then add 7 to it, and that's going to be Dwight's total speed that we have listed here. So great, we have our first 6 boxes, our first 2 rows filled in this table. That's the bare minimum requirement that we need for every single one of these problems. Now we can look here and see, do I have a potential total showing up? Meaning, am I adding distances together, rates together, or times together at all? Well, I can't add the times together because we're told they just travel at 2 hours total, so wouldn't make sense to have a total time there because the total time is just 2. But I'm not adding those times together, which is what this total row would represent. I'm not going to add the rates together because that doesn't exactly make too much sense here for what we're solving for, so we'll go ahead and leave that one. Am I adding the distances together? Yeah, I'm getting a total distance here of 234 miles. So, suddenly, this vertical column is matching up with this original column, or this little original equation that we made here. So let's rewrite each of these rows as specific equations now. So the equation for distance 1 is this r plus 7 times 2. And the second distance is going to be r times 2 as well. Now I can bring these things together and this general equation that we had all together in one single equation, which is going to be 234, the total distance that they traveled, being equal to distance 1, which is the distance that Dwight traveled, and I can write that in as r plus 7 times 2, plus distance 2, which is the distance that Mose traveled, which is going to be r times 2. And from here, I can solve this thing like I would any other Chapter 2 problem. So based on this, we know that Mose traveled at an average speed of 55 miles per hour, and we know that Dwight traveled at an average speed of 62 miles per hour. Now, I've had some people in the past ask about this, so a final clarifying point. If we're told there's an average speed that they traveled, we can reasonably assume that maybe they traveled a little bit faster than 55 and 62 and maybe a little bit slower than 55 and 62 across this total distance. But with the average speed, we're not going to worry about the specifics on when did they go 50 miles per hour versus 60 versus 70 versus 40. We don't care. We're not going to worry about that part too much. We're just going to worry about getting to 55 and 62, and we're going to call it there for this particular problem. In our third and final problem, we are told that Ron and Leslie leave Pawnee City Hall at the same time. Ron drives west at a speed of 72 miles per hour, and Leslie drives east at a speed of 76 miles per hour. How long will it take them to be 330 miles apart? So like we did with our previous problem, number 2, I'm going to go ahead and start with drawing a picture for this because there's some very important information to get from this, and I think it's always a good starting place to get some visual down for ourselves. Now you do not have to start with a visual if you don't want to, but I do think it is a good idea to have it showing up somewhere. Okay, so we have the City Hall listed here, and we have traveling to the west is Ron, as per the problem. And then traveling east is Leslie. Okay, we should put some labels in there. Now we are told that they leave at the same time. That's important for us to notice. That tells us something about time. So let's see, at same time. Write that in there. Okay. Or maybe you're in the boat of underline these things. Let's underline some of the stuff that's important that we've been given. Times, speeds, things like that. So, what else do we know about this? Well, we're being asked, how long will it take them to be 330 miles apart? So that does not mean how long until Ron has traveled 330 miles or how long until Leslie has traveled 330 miles. It's how long until the distance between them is 330 miles. Now, similar to our previous problem, do I know exactly how far Ron will have traveled? No, I have no idea what that distance will be. Do I know how far Leslie will have traveled? No, I have no idea how far that distance would be. Is there any indicator in the problem that would tell us that these two distances are going to be the same or different? Well, nothing says they're the same, so our only option then is to assume that these two distances are different. Now again, the picture that I drew, make this a D sub 2, the picture that I drew has City Hall in the middle, and I did that only for the sake of making it simple to draw this thing out. Again, when we get into the details of this problem, we are not given anything that says that these two distances are the same, they're different, they're this much different or bigger, smaller than the other. We have no idea about any specifics with these distances. All we know is that while these two distances are probably different, they should add up to be the total 330 miles to dictate how, or to show how far apart these two have traveled from one another. So fantastic. So we know the distances are probably different, but they add together to give us our total distance of 330 miles. So good, useful information. Let's go ahead and make our table and then make some equations out of this. So we had general equation starting off here. Like we did with our previous ones, we're going to list the distance as a column. We're going to list the rate as a column. And then we're going to list the time as a column as well. We have two sets of information, a distance, rate, time set that corresponds with Ron, so we'll list him as one of our rows. Then we have information regarding Leslie, so we'll put her as one of the other rows, or our second row here. And again, I think it's good habit. Let's go ahead and make a third potential row. We'll call this thing total. And I put the question mark at this total part here only because, as we saw with our first example, I don't always use this thing, and I don't always use these totals. So maybe I'm going to use it, and if so, I'll write something in. If I'm not, I'll just put the little line through it and not use it, like we saw with our first example. But let's start filling in some information that we know from the problem. We were told that they left Pawnee City Hall at the same time. So what does that tell me about the times? Well, I don't know the times, but they left at the same time, which means they've traveled for the same amount of time in opposite directions. So like we did with distance in, I think it was our first problem, I'm noting that while I don't know these two times, I know they are the exact same, so I can just list it as this single variable t. I don't need to put a little subscript in here to show that they are different from one another. Next, I'm looking at and seeing, okay, I've been told that Ron is driving 72 miles per hour, so we're going to put 72 in there. Leslie's traveling at 76 miles per hour, so I can fill that in here. And then what do I know about the distances? I know that they're, well, at the very least, not the same, or probably not the same, so I can fill in distance 1 and distance 2. I don't know either of them, but I know that they're probably not the same as one another. And then do I have any totals that are showing up here? Yeah, I've been told that they travel a total of 330 miles, and that's going to be these two distances adding together. It doesn't make sense necessarily to add the rates together, at least at this point in time, and it doesn't really make sense to add the times together because they travel for the same amount of time. So we can go ahead and put a little line through those and cancel those out. So let's make our two equations from this, this table. We have distance 1 is equal to 72r, or not r, t. And distance 2 is equal to 76 t. And now I can bring all of these together with our total equation. We're going to get 330 is equal to 72t plus 76t, and we can solve for the time from here. And from here, we're getting that time is equal to 2.2297, and it keeps on going on, and we've got a bunch of stuff for our decimals here. Let's go ahead and round our answer to 1 decimal place. So that means we're going to have a total time of 2.2 hours. So when we are going through problems like these, now we can see instances where we need to solve for time. But again, the visual, I think, goes a very long way with demonstrating, are the distances the same? Are they different? Making a note of that accordingly. Have they left at the same time or not? Because that could determine if these times are going to be different or the same from one another. And then bring it all together in one single equation that we can solve from here. As a quick recap of the material that we covered for today, we were working with uniform motion problems or application problems. We had our DIRT equation, distance equals rate times time, showing up for every single one of these problems. I recommend that we continue to write this out for ourselves with all of these problems as we're going through them, just so we know and get that repetition in of how to write it down and work with it accordingly. We also went through how to set up a table, how to label that and fill in the given information. I recommend also taking a bit of time in drawing out some drawing out some pictures, I should say, of the story problems. You saw how great and brilliant of an artist I am in all 3 of our examples, and I think that level of drawing and labeling is kind of the bare minimum that you need to be able to do to be able to go through and, I think, work with these types of problems. Obviously, you are not required in my class or otherwise to be drawing out these tables or drawing out the pictures like we are, but I do find it very helpful if you're ever unsure as to how to set these things up and how to start with them. Just don't try and do it all at once, and don't try rushing the process with these. Start slow, and then you can speed up from there. Then we had our 3 problems that we went through here. There it goes. We had our answers to each of those. So hopefully this has given you at least a good starting point or starting and launching point with working with these types of problems. You are going to see probably some weirder, different ones showing up, but I think if you stick to these main things that we did with each of these problems, you're going to be set up and good to go with just about all of them.